Welcome to the Air-Sea Fluxes from Space webinar series from OASIS. Today we have Eric DeSaro from the Applied Physics Laboratory in the School of Oceanography at the University of Washington, and he's going to talk about what's next for ocean submesoscale studies, multi-platform submesoscale sampling, and the S-mode experiment. I'll let you take it away, Eric.
Some variant. Okay, are you guys seeing my proper
That's
screen?
your presenter mode. You can swap displays.
Yeah, okay, it's never, there we go. Swap displays. Okay, now this should be correct, right?
Didn't swap.
It didn't swap. We'll try this. How about that?
That looks promising. Oops, it swapped back.
Okay.
We had it all perfect when you were getting started. Do you have an external monitor? You can just unplug, force it. It's always the trickiest part of the whole process.
What does use slideshow do?
Oh. Well, for those who are just logging in, we're working on getting the slides to display exactly correctly.
Technical problems. Try again. Okay, what do you see now?
That's your edit mode.
My edit mode, which we can live with if we have to, and that is.
That's correct.
Okay, don't touch anything. Okay. So in the last few years, I've been helping run a bunch of experiments, mostly S mode, and an experiment called Calypso. And I was thinking what to do for ocean sciences, and I said, let me step back and try to figure out, after all this, fooling around with ship scheduling and COVID and all sorts of stuff like that, where we should be going in submesoscale oceanography. And I gave this talk at Ocean Sciences, and this is a slower version of the 10-minute talk with a few little extra things added. And so I went and I pulled up all the articles I could find that had submesoscale in the title of the abstract the last 10 years, mostly focusing on the ones that had some combination of measurements and theory. And here's sort of what I learned. So what have we learned and what's next? And what I mean by learned is that there's something that we tried to think about that has both a good theoretical understanding and some data that validates that that's going on. And a good starting point for this is, so, well, why do we care? What are the things, why are we spending time studying submesoscales? Well, first, they exist. That's a good reason to study them. And then the theory and modeling suggests that these motions should stratify, stir, and mix the upper ocean and help set the upper ocean stratification, and are an important pathway to energy dissipation. Basically, what I'm saying in this talk is that, yes, number one, we know they exist. That's been 20 years of work. We don't need to prove that anymore. And it's these things which are harder questions, which is where we should be going. Of course, it's harder, and I'll talk about that. Okay, so go back. There we go. Oops, this way and that way. Okay, good. So what have we done in the last 20 years? Well, if you go back, this is more like 10 years ago, but never mind. This is a typical simulation from that period, and it's really quite striking. So it's a simulation of the Gulf Stream. Here's Cape Hatteras. Can you guys see my mouse? Hello. Can you see my mouse?
Yes.
Okay, thank you. So this is Cape Hatteras. It's a twist. That north is that way. This is the Gulf Stream going north, and it's hot. That's why it's red. Here's a Gulf Stream ring. Here's the Gulf Stream front. So if you're looking at temperature, this is sort of a mesoscale view of the world. You see things that you recognize, And of course, about say 20 years ago, we started to get models that were like kilometer resolution. This is a 500-meter ROMS run. And if you look at vorticity as opposed to surface temperature or quantities like that, you see something like is on the right. And it's really, really a remarkable image. I was tremendously struck by it when I saw it. What you see is a quantity with a blue spectrum as opposed to a red spectrum. And so that everything what you dominantly see is really small stuff. You see all these little vortices, little red vortices, that's cyclonic, that are evolving fast, being advected around fast, are skewed cyclonically, namely that the reds are brighter than the blues, but occupy less area. And there's clearly variations with the mesoscale. So here's the anticyclonic side of the Gulf Stream, and there's not much the mesoscale there. The cyclonic side has lots of mesoscale, and the Gulf Stream ring has all sorts of stuff in it. And the zeroth order question that I think we've been addressing for the last 20 years or so is this real? Do we really see this in the ocean? And the answer is yes. Here are some simple examples. We've known for a long time that if you look at things like chlorophyll or other small scale quantities, there are fronts in the ocean. They have very fine resolutions. That's a kilometer. That's a ship. This is in the Baltic Sea. There's a cyclone here, and then there's all these different fronts here. So that's sort of like what you see qualitatively. And if you have massive drifter arrays, this is from the Karth experiment, they rapidly form into these lines, and then the lines twist around like that. And so this is the same sort of thing. So that's good. And so we've seen lots of that now for the last, seen lots of that now for the last 20 years or so. And this is sort of a summary of what's been done, mostly with data, to address these questions. So 20 years of measurements from fairly simple things, simple arrays with a few elements or from sections. I think we've developed what I'm calling the classical submesoscale toolbox of metrics, things that we can compute, lots of people have computed, and seem to be robust and give us sensible values. So that's a classical set of things. Here's more or less what they are. If you can do derivative measurements, like here's an example of driving two ships a kilometer apart for 500 kilometers, you see some small scale stuff. You can take derivatives in both directions, so you can really do vorticity and divergence. You can look at spectra. Everybody knows about spectra. The spectra here are the black lines, and in all these curves here, this is the same region as the video I showed 2 slides back. The black is data. The red is what was in the model that I showed you. And say, hey, that's pretty good. The model is sort of -2. The spectrum is sort of -2 with a little bump there. There's some interesting results right away. Well, it's not -3, so it's not QG. And it's going down the scales, obviously, of about a kilometer or so. So that's a useful thing to do. Another set of useful things to do is to look at the PDFs. Here's a PDF of vorticity. You can see that it's skewed. In other words, there's a small number of large vortices. And on the anticyclonic side, it stops at -1. This is like what we saw in the movie. And in fact, in red is the video. It's a simulation. And then in gray is the data. Seems to agree pretty well. Similarly with divergence. So that's all good. And then there's these fancier things you can do. That's strain versus vorticity. And there it is for data. There it is for model. The patterns are similar. The way you read this is data that lies around here. Along here is a perfect front. Eddies are up here, so there's less of those. So there's lots of fronts, and it's sort of the same. So that's good. That's the statistic that we know about, and it's pretty solid. Another class of such statistics have to do with looking at potential vorticity. If you have negative PV, usually that's found when the wind is in the same direction as the frontal velocities, or down front winds. This implies symmetric instability and enhanced dissipation. And here's some sections across the Gulf Stream north wall where it's blue, the PV is negative. And so you see some blue places, so the PV is negative, and you can see this very characteristic sign of symmetric instability, which are these equally spaced, slightly tilted isopycnals right at the surface. It's stratified, even though it's mixing fine. And you can see that these change a lot in a few hours. And that's also a characteristic. Like we saw in the video, things change a lot in a short period of time. And finally, what we've seen is that you can look at these statistics and you can see how they vary seasonally and geographically. This is from the osmosis experiment in the UK. And here you can see, for instance, the skewness of the vorticity. This curve over here increases near the surface and is larger in the winter than in the summer, which is what theory predicts. So this is a set of tools that we understand pretty well, set of metrics, and they agree reasonably well with models. So there really is a submesoscale. It looks a lot like the models. Check. That's good. But it's not the end of the story, of course. These are all pretty qualitative. You can't get rates out of these things. You can say that there's symmetric instability, but you can't say how strong it is compared to other things. So there's lots more things to do, which is what we should be doing in the future. Okay, there we go. So recently there've been a number of experiments that are quite a bit more than simple arrays or sections. And their characteristics are that they're multi-scale. There's enough measurements that we can measure on many scales, both submesoscale and mesoscale. The point is the submesoscale should vary with the mesoscale, and have combined a lot of different platforms. The problem is you just can't get measurements over all the space and time scales with one platform. So you use a lot of platforms along with remote sensing. This is from S-mode. And this is actually from the second intensive S-mode experiment in 2022, in which we had, this is off California, there's San Francisco, classic place. This is a temperature image. We had a mesoscale component where obviously you can see you could do regular sort of classic mesoscale along with altimetry. And we had a submesoscale component that at this particular time was focusing on that little region here. There's a zoom of that. I don't have a scale, but this is probably about 50 kilometers across, and that's like a kilometer, something like that. And here you can see you can see running around this little real-time movie. You can see a ship. We had 3 aircraft, they're not in this image. We had about 15 to 20 autonomous platforms of one sort or another doing various sorts of sampling. For example, there's 4 sail drones in a little box that I think is 3 kilometers across. There's some wave gliders that stay together about 1 kilometer apart, more or less in the same place, all in an interesting place. That's a sea surface temperature image. You can see there's a front that's going unstable here. So this is a big step forward in terms of measurements of a sort that we didn't have before. The last year of S-mode was actually during the SWAT CalVal period. So we have some of these measurements simultaneous with SWAT data. So that should be useful. Okay. So what do you do with multi-scale 4D measurements like that? Here's an example of showing the much more sophisticated things that you can do. I'm less interested in the results here than how you get to the results for the purposes of this talk. This is from a similar experiment called Calypso, which was in the Mediterranean, working with our Spanish colleagues and on a French ship, among other things. And this is near the Gulf of Lyon, where the deep convection happens, and it's on the edge of the deep convection, so that near the end of the winter, so that the deep convective chimney is going baroclinically unstable, and you get a whole lot of cyclonic and anticyclonic eddies associated with that baroclinicity. So this is off to the side of it, and this is a ocean color image of an elliptical eddy. So the eddy's going around like this, elliptical eddy, and it was spun off the deep convection region, is now with the water surrounding it being stratified. And so what we observed quite remarkably was that this elliptical eddy in the course of a few days, went from elliptical to a long skinny thing, and then it broke into 2 smaller eddies, which then moved along. And these are some mesoscale coherent vortices, and they last a long time. There was a bunch of vertical transport. Isopycnals moved 100 meters or something like that as this eddy broke up. And we had rapid ship surveying and a whole lot of drifters and gliders, though not here, and a lot of floats who are able to do the same sort of mapping that you can do on the mesoscale, but now on the submesoscale. This is work that Leo Middleton has been doing. And so you can map in 4D density and velocity and some biological quantities like chlorophyll and backscatter. And you can diagnose those like you would with a model. It's all data, but you can use it like a model, and you can diagnose. In this particular case, we were very interested in vertical velocity, and here's 4 different ways to get vertical velocity. These are streamlines, and so this is streamlines of the map velocity at some particular time, and you can see this elliptical eddy from the mapping. You can use the continuity equation, just do that divergence. At submesoscales, divergence is big, so you could actually use it. You don't have to pretend it's 0. You can use the buoyancy equation. You can use the vorticity equation, or you can pretend that this flow were quasi-geostrophic, and you can use the omega equation. And then you can plot over here. This is a plot of the RMS vertical velocity over the mapped domain as a function of time, as this eddy goes from being elliptical to breaking up. And it's elliptical here at the beginning, and then it's turning into this long skinny vortex about here, and then it breaks up and we get bored and we go someplace else. So these, the vertical velocities from continuity and from buoyancy and from vorticity are these curves here, and they're all pretty much the same. And they're sort of pretty big numbers, 20 meters a day RMS. Other numbers, obviously the peaks are bigger, and the omega equation is much lower. And I'm not going to emphasize what the dynamical implications are, but it's pretty clear that they're there. You can say, well, does it matter that the Rossby number is 1 here? And the answer is yes. It wouldn't do this if it was a QG eddy. All sorts of stuff like that you can diagnose. And in this case particularly, omega equation, which assumes QG doesn't agree with the other one. So this one's right, that one's wrong, this one's right, that one's wrong. And that tells you a lot about the dynamics, which is not what I'm talking about today. So given that, where should we go? And this is a long slide, but the hope is that I'll stop at the end of the slide. I have one more, and we can have some discussion. So let's go back to the goals of this. What are the overall goal effects of submesoscales? Well, they apparently increase the stratification of the upper ocean, therefore fight with boundary layer mixing to decide how strong the stratification is going to be. And they have their enhanced dissipation, so have implications for the ocean energy budget. So the questions you should be answering, maybe there's some other ones also, are can we address these issues with some analyses of various sorts? For doing that for the globe and over long periods of time, I don't see any way to address this issue other than having models that you trust. As I was just showing you, some of these issues may be experimentally accessible at smaller space and time scales, but not for the globe. So if indeed models are the only way to go to do this on large scales, then we need to make sure that the models are good. Okay, there's sort of a bit of a roadmap. So it's like, so how accurate are state-of-the-art models would be the next obvious questions. And in a short term, we have many good metrics. I just showed you a bit back. We have a classical toolbox of submesoscale metrics that we trust. Well, how well do the models predict these? If you run 2 models against them in the same place, you don't get exactly the same answer. So can we tell which one is right? Seems like a good short-term or medium-term goal. And then, of course, maybe there's better metrics because we have better data. We're going to get all sorts of interesting stuff from SWOT. And the obvious ones are fluxes in space and in wave number. The next slide is about that, but there'll be a pause after this. The question is, we're going to need some mesoscale parameterizations. You're not going to run the world at submesoscales for long periods of time, just given computer resources for a while. So we need these. There is a existing submesoscale parameterizations, which has been tested quite a bit. This is called something like the Emily scheme. It's Baylor Fox Kemper's early work of 3 papers, but it isn't the final answer. It's probably perfect. It's probably perfectly good. And in many, well, first of all, no parameterization is the final answer because nothing's perfect. So there's always room for improvement. But in particular, it's pretty clear from looking at the behavior of models that the rates of baroclinic instability, which is what this is a model of, a parameterization of, in the presence of wind stress and buoyancy fluxes, really modifies the baroclinic instability quite a bit. In particular, if the wind is in what's called an upfront direction, it wipes out the front without needing baroclinic instability, and there isn't any MLE. So there's a lot of stuff that could be done to make this better and test it. And then finally, the question is, how do we make the models better? Well, the obvious answer is you improve the physics, and there's plenty of physics to be improved. In particular, the surface submesoscale, which what I'm talking about here, not the stuff on the bottom, is in the ocean boundary layer. So all the things that affect the ocean boundary layer, surface waves, boundary layer turbulence with its complexities, and the atmosphere, they all are interacting with the submesoscale. And that seems to me to be the place where the models are pretty deficient now, and there's lots of room for improvement. So, and just a final thing, there are still surprises out there. There's lots of room for exploring in both the real and the simulated oceans. And so maybe it shouldn't all be that directed. There's new things to just see by looking hard. So I'm going to stop here. There's one more slide and open this up for discussions. And when we run out, when that slows down, I can put up the next slide.
Well, thank you. Questions or discussion points?
Comments? Other editorial comments?
Well, if I can start, you showed this really nice vertical velocity comparison.
Yeah.
Where you showed the RMSE.
Right.
Or RMS vertical velocity. But looking at the maps, it looks like the 3 that sort of agree in the RMS don't necessarily agree. What's the correlation between them?
I don't know. I didn't do this. And this was pulled off, a Calypso progress update meeting. So,
So yeah, we have to interrogate Leo Middleton.
Yeah, that's right. So there have been similar things done with gliders that Dan Rudnick's group has done, which actually are published papers, and they do these similar comparisons. And clearly vorticity is noisier noisier. And but I believe that the answer was that accounting for the noise, they all give similar results because they're all similar order equations. So I didn't do it, so.
Well, thanks. Yolanda has her hand up.
Yeah, thanks, Sarah. Great talk or introduction to your talk. I don't know if you said you have more slides, but I just wondered, so right now I have the impression that the frontal regions and these submesoscale representations are the same everywhere. I mean, you're showing mainly mid-latitude examples, and I'm just wondering if you think, or if in your lit review or and in your own experience, that the agreement or lack thereof is similar everywhere. Are there areas of the world where this is different? I mean, do we need to think about that?
There's no question that there's lots of geographical variability. Sort of to lowest, I haven't got the slides, I'll just leave this one up. Sort of the lowest order theoretical prediction is that the submesoscales are energized by the forward cascade of potential energy. In other words, you take dense water from 2 different places that are far away, bring them together, make a front, and the available potential energy in that front goes unstable, and that makes small scale submesoscale. That's and so it depends a whole lot on how much local density gradients you have available, and also very much on how deep how deep the fronts are, which is sort of how deep the mixed layers are. This area here in this picture was very energetic because in a deep convection region, the mixed layers can be really deep, and so there's a lot of distance for the heavier water to fall underneath the light water, to put it that way. So that's an example of strong submesoscales. Another example of really strong submesoscales is where you have fresh water coming into the stratified ocean, either in places where there's huge river inputs like the Bay of Bengal, or in coastal regions. It's no surprise to coastal people that there's submesoscales. They've known that forever. And so there's lots and lots of geographical variability. The Arctic is another example of that because there's fresh water involved and therefore big density gradients. And then there are places where there's not that much mesoscale and things are going to be weaker. And there's some nice global models which speak to this sort of variability. But I think we're still a ways from mapping that out. I think SWOT will go a long way to doing that because it's so global. That's sort of an answer.
Okay, yeah, thank you.
And it isn't necessarily that, the submesoscale you get out of a 200-meter deep mixed layer isn't necessarily the same as the submesoscale that you get out of a 10-meter deep mixed layer. So there's going to be a lot of interesting phenomenology.
Yeah, and that's what I wondered is like when we say we're going to improve parameterizations, are we going to find that there's not one parameterization fits all kind of thing? Yeah.
Yep, that's right.
Okay. Yep.
David Wolf has
Hi.
a hand up.
Hello, thank you, Eric. I was just wondering about, in terms of confronting models with data,
Yeah.
whether you see a role for Earth observation, and if you do, what would you like to see on a satellite in the next 10 years that would help?
Oh, well, we're talking about much of the motivation for this seminar series, but be that as it may, and I'm biased here, so I'm just tell you my opinion. One of the things that was a huge emphasis in S mode was looking at the near surface velocities. And because we had aircraft remote sensing measuring surface velocities, down to sort of 100 meters or ish scales. This is Doppler scat, and that data was just really remarkable what you could see, and so it seems to me that Odyssey, which is supposed to do that globally from space, would really be a real game changer, particularly in conjunction with what you can get from things like SWOT or its follow-ons by the time any of this happens, because then you have measurements of both the potential energy, namely the sea surface height, and the kinetic energy, namely the velocities, and it's those interplays that are so important for this. So that would be my answer, and though other people there may be other equally good answers, but having velocity at these scales remotely and globally would really be a wonderful thing.
Well, I wanted to hear your answer, so that's great, Eric. Thanks very much.
Yeah.
Megan Cronin has her hand up.
Yeah, hi. Thanks. Great. It's really exciting to see all of this. With such a big cluster of platforms, obviously, when you bring platforms like that together and you're calculating the mean, the closer they are, and as a cluster, you get a more robust mean. But in fact, the derivatives and the errors in the derivatives can become really tricky because as you get closer, the errors in the derivatives kind of go up.
No, that's wrong.
So
that's
no?
the key. That's the key thing. That's the key thing. The spectra that because we're so used to thinking about things like temperature, which have red spectra, meaning that the biggest signals are at the big scale, as in the figure on the right here. But in fact, for derivative quantities like vorticity, you look at this thing, where is most of the energy in this picture? And it's at the small scales. The closer you put them together down to some scale of a few hundred meters, the more signal there is. In other words, if I look, I don't know if you could, if I look over that, all the derivatives are on a very small scale. They're in these lines. And so if you take them far apart, the number is smaller. If you put the measurements closer together, they're bigger. So if we're measuring derivative quantities, things with white or blue spectrum, the closer you put the sensors together, the more signal there is, until, of course, they're right on top, until they're right close to each other. I mean, another example of that, if you just want to see big velocity differences in the ocean, put something 100 meters apart. You'll see huge velocity differences. That's called surface waves. Oh, that wasn't the velocity I wanted. Well, I know, but it's a real velocity. And that's because those things have a peak at very high wave numbers. So it's very counterintuitive. And the measurement technique you need to measure both the red spectrum things and the blue spectrum things are different.
But I guess my point
Yeah.
is that there's a trade-off, because if each of the platforms has an independent error, as you bring them together, the slopes between those 2 points can, you can get the estimated derivative from those with the errors goes up as the delta of the derivative goes smaller.
Right, but the signal for quantities with blue spectrum, the signal goes up faster than the error.
Okay.
Eric, we should also add that in S mode, we worked really hard on velocity accuracy to make sure that our gradients aren't dominated by errors.
Yeah. I'm certainly not saying you shouldn't pay attention to errors.
Yeah, I'm just wondering if there's some new way of approaching this, since you are trying to get smaller, and so the errors could go up.
Well, Megan, we did an error budget if you have platforms separated by 1 kilometer and you have 1 centimeter per second accuracy, you can resolve, easily these signals. Sort of your error is kind of 10% of the signal.
Mm-hmm.
Or another way of saying it is that these red things, there's no color bar here, but the red dots in vorticity are like 2 or 3 F, and 2 or 3 F is 10 to the minus 5, which means 10 to the minus 5, and that means in a kilometer it's 10 centimeters a second. So that's not hard to see. But you don't see it most of the time. Most of the time you're in these blue regions where there's not much to see. It's only every once in a while. That's the weird statistics of this.
So how do you know when you're in the blue region or the blue region with sharp red? When you're taking your data?
By definition, it's when you see
Okay,
see something. I mean,
so it'll just be a spike. You're saying, yeah, okay.
yeah, that's what. Yeah, you drive.
Intermittency.
Yeah, if you drive along here, you'll see hardly any gradients, and there'll be a big gradient. Then there'll be hardly any gradients, hardly any gradients, hardly any gradients, and then a big gradient.
Fine, okay.
Which is why you have to work, which is why these experiments are so difficult, because in this picture, if you're over here, there's not much to see. If you're here, there's a lot to see.
Mm.
Well, how do you find this as opposed to that? That's the hard part of doing this.
Is that the temperature behind there? Is that what you're?
Yeah, that's a satellite SST, but we have way better SST from aircraft, but it's not in this little picture.
And is SST the main way you would see the mesoscale. I mean, what about salinity? I mean, the net thing you want to see is density, right?
Yeah, well, we'd love to have high resolution remote sense density. That would be really good. That's another thing to add to your list. There isn't high resolution. The salinity, remote sensing salinity doesn't have enough resolution. The remote sensing temperature and also ocean colors. I just see what, here's temperature, right? We can see the gradients there. And there's ocean color, which isn't temperature, so it's better than nothing. So sometimes color is the best thing to use, and sometimes temperature is, and sometimes they're both there, but not that often. So there are probably some hyperspectral things. So we'll probably get something out of PACE. And for these sort of studies.
If I can come back to David Wolf's question.
Yeah.
You mentioned the possibility of Odyssey and the value of SWOT. I'm wondering about Harmony, which will give, if you're familiar with it, and there probably is somebody online who can say exactly what Harmony will do. But it's a SAR mode that will give winds and currents in small areas that happen to be sampled by its 3 SAR receivers.
Yes, Aaron,
So-
hi, this is Ernesto. Yeah, you're absolutely right. Odyssey will be great, but the resolutions for these things will be somewhere around 10 to 20 kilometers globally. So there is already a group of people, and we welcome all the participants, thinking about what the follow-on to SWOT might be. And right now it's called SWOT Loco, where names will change probably. But it incorporates SWOT type topography, a high resolution, maybe wider swaths for better spatial and temporal resolution, together with a velocity mode that would have hundreds of meters scale velocities together with wave imaging. So that's probably something that at least is afloat in the community for the next generation. Odyssey is hopefully in the near future, but it will take some time.
Thanks, Ernesto. And maybe that means there's some room for people to think about how to knit these together. If Odyssey provides global scale observations, but Harmony and SWOT provide higher resolution, how do you put them together to gain a picture of all scale?
I hear silence. Let me ding a little bit more. This is definitely getting into ocean measurement nerddom, but okay, here we go. I said that there were 2 things that we care a lot about. One is stratification and one is energy budgets. And suppose we wanted to have some metrics that talked about, what are rates as opposed to just what are quantities. And the obvious metric for stratification would be vertical buoyancy flux. And the obvious metric for energy budgets is spectral energy flux. And I want to talk a little bit about, in particular, the context of submesoscale measurements, that there's some pretty serious issues with using these, I think. And this is food for thought. So the vertical buoyancy flux, although people also often think of it as what causes stratification or unstratification, and that's true, is most fundamentally perhaps the exchange rate between available energy and kinetic energy. That's what it is. And the problem is that almost all ocean processes contribute to this rate, and many of them are a lot more energetic than the submesoscales. In other words, if you measure the vertical, the same thing that's happened with ocean mixing measurements. The textbooks all say you should be measuring vertical buoyancy flux, but if you measure vertical buoyancy flux in the ocean, you see vertical buoyancy fluxes from mesoscale eddies, which are pretty big, from internal waves, and it makes it really hard to interpret. And so the issue is, how in either of these measures do we isolate submesoscale components? And one of the characteristics, good and bad, of submesoscales is that they are highly intermittent in both space and time. In other words, you might think of them as a bunch of time-varying fronts. And another really important thing is that they tend to be slant. In other words, their motions. In other words, here's an example. This is also from the Mediterranean. This is depth, this is time, it's a section with a scale of about 10 or 20 kilometers. This is a figure from Mara Freilich's paper. The lines are isopycnals, and the color is backscatter. So it's an optical dye. And you can see that there's high values near the surface, and then they get carried down along these isopycnals. So that's motion sliding along isopycnals. And this is irreversible, unlike a wave motion, because it's very unlikely that you can slide this backwards all the way up and reform it. So the question is, how do you get the component of vertical buoyancy flux that's associated with this and not associated with just the isopycnals moving up and down? And just to talk about that problem, go down here. Well, the change in available potential energy is sort of n squared times displacement squared times RMS displacement squared times area. And keeping the n constant, if you have a mesoscale motion 100 kilometers by 100 kilometers with a vertical displacement of 1 meter, you have this everywhere all the time. It's got the same available potential energy as a submesoscale front, which is 2 kilometers wide by 20 kilometers wide with a displacement of 20 meters. That's the same amount of buoyancy flux in those two. So you're going to, this one, if this is the one you want it, you're going to be heavily contaminated by that one. So that's sort of the nature of the problem. There's a similar problem for energy budgets. There's been a lot of new work on doing spectral energy fluxes. We've heard a lot of it at Ocean Sciences. I can recommend a talk from Ocean Sciences. They're all online still until May. You can listen to your favorite Ocean Sciences talk again. There's a very good one by Bela Fox-Kemper who talked about this issue, all the different new methods that have been developed. Spectral energy fluxes are the third moment of a highly intermittent process. Those are unlikely to converge very rapidly. For the data that we took in the Gulf Stream, the 2 ships, we computed the third moment. It was entirely dominated by one front in the middle of a 500-kilometer run. So it's a hard statistical problem. And then the other issue is this has all been done with kinetic energy fluxes, but but available potential energy flux is probably even more important, and nobody seems to be talking about that much recently. One approach, and I'm just putting this up as a type of clever things that maybe we should be doing, is this is one of these diagrams of strain in the vertical and vorticity in the horizontal that I showed you back before, where the data runs along these lines, and that's the using coarse graining methods. I believe this is Hector Torres's plot, but I'm not sure where I got it. This is the nonlinear kinetic energy flux. And you can see it all lives out here at high vorticities and high strains, which is exactly the submesoscale part. So instead of computing the vertical buoyancy flux everywhere, you might want to compute it, say, in that box over there, and that would probably be something which would isolate the submesoscales. So that's just some thoughts that we really do need metrics which are much more quantitative that we can use and much more focused on dynamics that we can use to compare models and observations, but it's not clear to me that the obvious metrics are going to be very useful. So I don't know if that's way too nerdy, but it might have some discussion, may promote some discussion.
Well, comments on this?
Too nerdy.
You emphasized, I have a question here.
Yeah.
You emphasized distinguishing the submesoscale from everything else.
Right.
If everything else is more energetic than the submesoscale, do you have to distinguish them?
Well, that gets to the question, why you're doing this in the first place. And the answer is for some particular parts of the oceanography, namely, as I said, the stratification and what the ocean energy budget is, the submesoscale may be playing a really important role. That an ocean without that would be different. So that's the argument, is why you try to pull out that dynamics, which is sort of, I mean, that's what process studies try to do, is that sort of thing. So I mean, another way of phrasing the question I'm posing is, what should the purposes of process studies be? both Calypso and S-mode were quite focused on, depending on what words you want to use, vertical transport, Lagrangian trajectory, 3D Lagrangian trajectories. Those are all things which have qualities of vertical buoyancy flux. And then internally, we've been having a lot of discussions as to which things you should measure, and that's what prompted this line of thought.
So there is an extensive discussion in the chat.
Oh, maybe you can. I can't read. This
So,
is read chat at the same
and
time.
maybe Megan pointed out, it seems like you have to be very careful with the sampling strategy for ADCPs when you're doing a cluster study for submesoscale gradients, where you're doing continuous sampling, 2-minute averages, 5-minute averages. And then Tom responded, and I can keep reading or people can pipe up. The wave gliders and sail drones were sampling continuously at 1 Hertz, but you have to average to about 5 minutes to suppress surface wave orbital velocities. For S-mode, we did a study of the accuracy we can achieve with motion compensated ADCP measurements on wave gliders. And then Luke Linnell went on, in addition to sampling strategy, we were also very careful in the motion compensation of ADCP observations for the wave gliders.
Yeah, Luke and I said the same thing at the same time, basically.
Yeah. And Megan pointed out, if you have power constraints and cannot do continuous sampling, is it better to have the average longer, 5 minutes, but less frequent, or shorter, 2 minutes, but more frequent?
I will give an answer that is very, very much from where I grew up in Normandy. It depends. It really depends what you're sampling.
Can you elaborate on the "it depends"?
Well, I mean, it depends on the spatial temporal availability of what you're observing. And it really depends.
But Megan, on your specific question about averaging out surface waves,
Yeah.
it's something I've thought a lot about for moorings too, and it turns out that there's, if you average 5 1-minute averages, you're going to get something very similar to what you would get with a single 5-minute block. It's not identical because the a 5-minute block slightly better filters the waves, but in practice it's not that much of a difference. So I would go for shorter bursts of if you're power limited.
Wait, you would go for
More
the 1 hour, 5-minute?
No, I would go for 5 1-minute bursts, because you might, I mean, it's only slightly worse at suppressing surface waves, but you retain some temporal resolution.
Yeah, and the thing to consider if you're trying to save some power is not only the length of the burst, but how many pings you're averaging. I mean, do you need to go to 0.5, to 2 Hertz kind of sampling versus, having a ping every second or something like this? So we've experimented with this a little bit. The most important part is to make sure that the ADCP data that you utilize are carefully motion compensated with ping by ping by using an external GPS IMU system, and that's crucial.
Right. Yes, got you on that one. Okay.
So Tom, when you say, sorry, I
Go ahead. Go
going to
ahead.
jump in 2 seconds here. So when you say 5 1-minute averages, how far apart are you? Because she's talking about, Megan is asking about over an hour, right? So we could do 5 minutes at the top of every hour, but you're saying 1 minute averages like spaced around the hour. Is that how I'm understanding your comment?
Yeah, but I mean, this, I think we're slicing it pretty thin here. But like for a mooring, for example, if you have to choose between 2 samples per hour and 1 sample per hour, and you can afford to do the same number of pings, I would do the, 2 ensembles per hour, that is. I would do that just because you have a chance of resolving some energetic high frequency signals that way.
Yeah.
Okay.
And
Yeah.
you can
Oh, good,
average them
because that
together
is
if you
what we're
want.
doing.
Yeah,
Good.
okay, thanks. Yeah, I don't mean to get too much into the weeds here, but I just wanted to clarify that one comment. Thank you.
But it is important when if you're doing these kind of mesoscale studies, that you really have to be very, really got to beat down those errors.
It has an interesting corollary for thinking about satellite observing too. What do you, to what extent do you optimize sampling versus resolution? And maybe not one anybody's prepared to answer quite yet.
No, but it's important to think about it.
Yeah.
Because that applies for, for any of those observational platforms that don't provide a snapshot, either in space or time.
Mhm. Well, are there any further discussion points, questions or comments? If not, we will thank Eric for stimulating a really great discussion and for a wonderful talk. And we'll see you the next time.
All right.
All right.